Hello students, in this video we'll prove existence and uniqueness of the wave equation with dissipation. Let's consider the PDE, UTT is equal to c squared uxx plus alpha ut, with ux0 being a function g of x and utx0 being a function h of x. We're going to assume that alpha is a positive constant over here, so alpha is greater than 0, and we're going to assume that g and h are compactly supported. Just for the sake of argument, to make our integration by parts calculations simpler, right? And so our goal is to show that there's a unique solution to this, right? So our goal, show that there is a unique solution to this problem, if one exists, right? Okay, good. All right, so the classical way to prove the existence of these things, to prove the uniqueness of these things, is to use energy inequality, right? And so let me explain that. So what we're going to do is we're going to define an energy in this. So define the energy functional. Okay, the energy functional is E of t. Is going to be 1/2 the integral over r, okay, of the function ut x t quantity squared plus c squared ux x t squared dx. Okay, so what these things are these things are really potential and kinetic energies, right? So I have potential and kinetic energies, I add them up and I average them, and that gives me this energy over here, okay? And so now, of course, what we want to show is we want to show this energy is conserved in the system, right? Or in fact, the energy is going to dissipate in the system, right? So now, let's take the derivative of the energy. The derivative of the energy is therefore what? Bringing these powers of 2 down is just going to cancel that 1/2 integral over r. And then we'll have what? We'll have a utt of x of t, ut of x of t, and then plus c squared, and then a what? Then a ux t, x of t, u, then t, just ux, right? Okay. Good. Dx. Now I'm going to take this, I'm going to integrate by parts on this term over here. So on this term over here, we're going to do that integral by parts. So take this integral over here and integrate this term, integrate this by parts. Okay, excellent. What are we going to do if we do so? Well, we're going to take this x derivative over here and pass it over there, right? And since by the compactly supported assumption, the boundary terms go to 0, and this is going to be the integral over r of just utt, x of t, ut of x, okay? And then what? And then minus c squared ut xt, and then a uxx xt dx, okay? Now, they have a common factor of utt, that's great, pull that out. And then I have utt minus c squared uxx. Utt minus c squared uxx, that's negative alpha ut, right? So this integral over here is just negative integral of what? There's a factor of ut, that was common to both of them. Ut, I'll just suppress the variables now. Ut, and then I have a what? Then I have an alpha ut dx, which is what? Which is negative the integral over r of alpha, and then ut x of t quantity squared dx. And that quantity is less than or equal to 0, right? By assumption, because I'm assuming that alpha is positive. Now, moreover, I know that it's less than 0, so the derivative, and I know so the energy is what? So the energy is going down, right? So in other words, that says the energy is a decreasing function, right? So this says the energy is a decreasing function. Energy is decreasing or non-increasing. And that's why we say that this term over here, that's why we say this term over here, this alpha U, induces dissipation, because it's a dissipation. There could potentially be a dissipation of energy. Either energy is conserved or energy is going to dissipate, right? There's nothing else. You can't increase the energy in the system, right? So energy is not increasing. That's great, because now what we're going to do is the following. So now we can say, okay, notice that if I have two solutions, if we're given U1 and U2 solutions, in other words, they both solve this PDE, they solve that initial value problem, then W is U1 minus U2 solves star with no boundary conditions, right? With W of x of 0 equals Wx, x 0, and they both equal 0, right? And so that says that W initially has energy 0. So in other words, the energy relative to W at time 0 is equal to 0. And that says the energy of W for all time is it's decreasing, and it's always bigger than or equal to 0, so it has to be equal to 0 for all time. So that says that the square, it says that what? It says that the t derivative squared, the x derivative squared is always equal to 0, which forces those to be what? Forces those to be 0. And that says that W has to be identically equal to 0. So W is identically equal to 0. And therefore what? And therefore U1 is equal to U2 for all times, right? In other words, U1 and U2 start off with the same thing and they have to agree for all time. Therefore, the solution to this problem is unique, right? And so we can see over here that the energy, because what happens with the energy is you take two solutions for uniqueness and then you subtract them. If it's a linear PDE, you're still gonna have a solution. And then that difference of solutions will have 0 boundary conditions. If it has 0 boundary conditions, then that tells you, or 0 initial conditions rather, if it has 0 initial conditions tells you that the initial energy is 0. If the energy is decreasing, the energy starts at 0 and it can't go negative. So that means that the energy has to stay at 0. If the energy is at 0, that's going to force this positive quantity over here to be identically equal to 0, which forces W itself to be 0. W being 0 means that the two solutions have to agree. A very standard way of proving that there's a unique solution to a problem is via this energy method, and we'll see this in further videos. Thank you very much.